you have to set it in the right context, which is the 20th century, the last century, and that really was the century of fundamental physics. So it's a little hard to define fundamental physics, and I don't want to sink into it in too much detail, but it means something pretty specific, at least for a bunch of us. So fundamental sounds good, but it doesn't mean that every good kind of physics is fundamental physics. Fundamental physics, the dream of it would be something like you could find some equations that you could write on a postcard that would be the laws of physics, and then in principle, from those you could calculate everything that you can calculate using laws of physics. So that in principle carries a lot of weight there because, for example, we know enough physics to, in principle, calculate the melting point of water. We know the physics that governs water well enough to do that, but it's actually incredibly hard to do that. So in principle, bears a lot of weight there. But anyway, people going into physics in the 20th century were, I think, looking for some fundamental laws that govern the cosmos in that carefully delimited sense. And if you think about the history, you'll see what I mean. So in 1897, Thomson discovered electrons experimentally by making what we would now call maybe like a vacuum tube or a cathode ray tube. It found that you could shoot a beam of little particles, which turned out to be electrons. Then in 1905, Einstein showed that light is made of particles. Theoretically, he made calculations that showed that light is made of particles that we later called photons. And it was quite a while before people really believed that. It took a lot of experiments and getting used to the idea that light was made of particles. Now, 1905 was a special year because also in 1905, Einstein showed how to prove that matter is made of atoms. He showed that if you watch carefully how pollen wiggles around when it's in water, it's being buffeted by little atoms, and you can use the statistics of how it's wiggling around to figure out the size of atoms. And then shortly after that, someone did the experiment and basically calculated how many atoms there are, for example, in a cubic centimeter of water. It's sort of amazing to realize it, but in 1905, there were still a lot of good scientists, physicists, who didn't believe in atoms, but this sort of clinched it. Also in 1905, he had a very busy year, he unified space and time. He showed that space and time are two aspects of the same thing, and that means also that, for example, energy and momentum are two aspects of the same thing. E equals mc squared is a spin-off of that. All of this follows from the unity of space and time in his theory called special relativity. In 1911, Rutherford discovered that atoms contain a much smaller thing in the center of them called a nucleus. Most of the mass of an atom is in a tiny little particle in the middle. These orange guys here are experimental discoveries that were unexpected, that people hadn't really expected from any theory, whereas the green ones are theoretical predictions that were later borne out. In 1915, Einstein completed his work on space-time by showing that gravity is really just the bending of space and time. And so his theory of general relativity, which later on was used to predict things like black holes and the Big Bang, was found then. So this is an amazing change, if you think about it, in just, I guess, 18 years of our worldview. Our whole worldview was rapidly changing at that time. And then there was a lot of work trying to understand the nature of atoms after people got used to the idea of them, but I won't go through all that. In 1927, Schrödinger came up with Schrödinger's equation, which is a precise equation describing how all particles are also waves, and also vice versa, all waves are particles. And that's called quantum mechanics, and that has had a huge impact, basically. All our understanding of matter and chemistry is now owed to quantum mechanics. And it continues on from there and became more abstruse, I might say, after that, because in some sense, this is most of what you need to understand the world that we can see around us in this auditorium. But it continued on into deeper and deeper understanding of physics until roughly around 1980, which is, I think, around the time when the last theoretical predictions have been made, which were subsequently verified by experiment. So in other words, people have continued making predictions after 1980. You've heard of string theory, and there are lots of other kinds of theories, but none of those theories of fundamental physics made any predictions after 1980 that have been verified since then. And there are only a few of these orange experimental breakthroughs in fundamental physics since 1980. The two that I keep in mind the most are the discovery that neutrinos can turn into other kinds of neutrinos, and also the discovery that the expansion of the universe is accelerating, it's speeding up. That's often called the theory of dark energy. We don't really know what dark energy is, but that would be the simplest explanation of why the universe is expanding faster and faster. But the main thing is that was an unexpected discovery that was just an empirical discovery. People just studied galaxies until it became clear that that was true. But for people like me who are theoretical physicists trying to predict new things, that is, these kind of green discoveries, life has been pretty tough since 1980. I went to grad school in the 80s, and well, so you can see that it's a very different situation now. And there's a lot of questions about why that is the case. And I don't think I want to delve too much into why that's the case, because, if you're not discovering things, it's sort of hard to explain why you're not discovering things, right? Maybe I'm not smart enough, or maybe there's nothing to discover, I don't know. But anyway, the fundamental physics that was discovered in the 20th century completely transformed the world. For example, no one would have expected at the beginning of that century that we could turn sand into silicon chips that could compute, and we could make tiny little computers that we could fit in a cell phone, and that we'd all be walking around carrying high-powered computers made of basically silicon taken out of sand. Also, we learned how to make nuclear weapons that can destroy entire cities. We had this tragic situation that continued on to make the atomic bomb, and then it was used on Japan, completely devastating the city and completely changing the face of world history, so that now the threat of nuclear destruction is always sort of hanging like a sword of Damocles over us in any sort of conflict. There were massive effects, in short, on the whole world from the discoveries of fundamental physics in the 20th century. And let me not try to get into too much of what these discoveries were, but let me just give you like a quick tour of how we shrunk inwards, looking at ever smaller things and figuring out how they worked. So first we figured out how atoms work. This is actually a photograph of an individual hydrogen atom. A hydrogen atom is the simplest kind of atom. It has a proton, a single proton as its nucleus, and a single electron going around it. The marvel of quantum mechanics is that that electron doesn't really have a definite location. It's just a cloud of probabilities, but if you look to see where it is, you may or may not see it there. And so if you look over and over again to see where the electron is, you'll get different answers. And if you keep track of those answers and you draw little dots for each time you see it here, 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 you'll get a picture of a cloud. And so this cloud is a picture of that for a specific hydrogen atom in a particular energy level that produces this kind of nice sort of double wave pattern. So this is a real thing here. Atoms are about 1 million times smaller than the width of a human hair, if you want to get some sense for how much you have to zoom in before you can see individual atoms with the help of equipment. But then, of course, the question became, well, what's in that nucleus, or what's in the electron? But it turns out the nuclei are more, you can make more progress understanding them, because although the hydrogen just has a single proton in its nucleus, other atoms have a bunch of protons and also particles called neutrons in their nucleus. So the nucleus is a more interesting blob of stuff. And so nuclear physics came about, and we figured out eventually how the nucleus works. This is not a photograph. This is like an artist's conception. I like it because it's more realistic than a lot of cartoon pictures you might see of a nucleus. So you see it's very blobby. It's a silicon nucleus, so let's see, oh God, now I'm in trouble. I think it has a bunch of protons and neutrons in it. I'm trying to remember the periodic table. I don't want to do that. I don't want to get caught on tape saying the wrong number of protons and neutrons. It doesn't matter. I didn't have to say it was silicon. I could have said it was carbon, and you would have believed me, right? But because all particles are waves, they're not just like a little blob sitting there, like little billiard balls or something. There's just a wave function of probability of finding them in different places. And so that's what you're seeing here. And so this is about 10,000 times smaller than the hydrogen atom that I showed you before. And the math required to describe how this works is much more complicated than the math that Schrödinger came up with that describes the hydrogen atom. So it took a lot of work throughout the century to reach the point of understanding nuclei. And then we figured out how the individual protons and neutrons work. We figured out that each one of those is made of 3 particles called quarks, which are held together by particle/waves called gluons. And this picture is even farther from being an actual photograph. This is an artist's conception, and I'm a little bit less happy with this one than the previous one. I think someone should draw a better one, but I couldn't find a better one anywhere. So you sort of vaguely see there's a red, a green, and a blue thing there. That's because quarks have qualities associated to them that are metaphorically called color. That has nothing to do with color. It's just people ran out of names for things, and they say they're either red, green, or blue, but they don't really look red, green, or blue. And also, they don't look so big and fat and blobby, and they don't have like little lines connecting them like that. It's much more tricky to draw than even this, but this is pretty good. And quarks are much smaller than a nucleus, so we know for sure that they have to be at least 100,000 times smaller than a nucleus. So basically, for all we know, they are points. They're perfect mathematical points, but in the sense that they're particles that are points, but their probability wave function of finding them is all smeared out. But we don't know for sure that they're points because there's nothing you can really do to be sure that something is infinitely small. So we just keep trying harder and harder to see if there's any structure to these guys, these quarks, and we just haven't found anything yet. So all I can say is that they have to be at least that small, but they could be even smaller. And that's about where we are now. We don't know anything that quarks are made of, and we don't know anything that the electron is made of. And we have this beautiful theory called the Standard Model that describes how quarks and electrons and other particles like neutrinos interact with each other. And it seems to work awfully well. And people have been working very hard to try to find any deviation from the Standard Model. They have this enormous particle collider on the border of Switzerland and France trying to look for deviations from the Standard Model, and they haven't found any there. So that's sort of where it stands as far as the constituents of matter, although we also know that there are mysterious things going on. You may have heard of dark matter. No one knows really what it is or even if it is, but we know that galaxies are spinning in ways that they shouldn't if there is only the matter we saw. So there are mysteries, but they aren't mysteries that we have been able to make much progress on recently by doing experiments on Earth.